Okay, let's try this again. Is that better? Okay. Welcome to week 10 of IT 241. This week we're going to be talking about I/O systems. Okay, sorry, I forgot to turn my microphone on. I've been talking here to myself. Before we get into our material for this week, we're going to be looking at the exercise from week 9. And the exercise from week 9, we were looking at how far the disk heads had to travel to service a certain number of requests on the hard drive. And this is important for performance reasons. It depends, how much the disk heads are moving. If they're moving a lot, it's going to actually slow down your performance when you're reading from disk, because it just takes time for the heads to move in and out of the disk, as well as for the proper sector to get aligned underneath the head as the disk platters are spinning. So we have a disk drive that has 5,000 cylinders, numbered from 0 to 4,999. The drive's currently serving request at cylinder 2150, and the previous request was at cylinder 1805. This is important because we need to know what direction those heads are now moving on the disk to know how far it needs to go to get to the next cylinder to be serviced. In this case, we're moving from the lower number tracks to the higher number tracks. The queue is just the request that the operating system got for what cylinders needed to be read next on that hard drive. So this queue is in, first out order. And what we want to do is start from the current head position, calculate the total distance in cylinders that the disk arm is going to move so that it satisfies all the requests that are currently in the queue. And we're going to look at these different disk scheduling algorithms: first come, first served, shortest seek time first, scan, look, circular scan, and circular look. The important thing in this problem was to figure out the order in which it would access the different cylinders on the hard drive. So we know that our current head position is at cylinder 2150, and the previous one, as I said before, started at 1805, so we know we're moving from lower numbers to higher numbers. But in first come, first serve, that really doesn't matter. We simply service the queue in the order it came in. That's exactly right, Monera. In first come, first serve, it doesn't matter. However these requests come in, that's the order that we service the requests. So the first cylinder we need to get to is cylinder 2069. So we're moving from 2150 to 2069, and that gives us a distance of 81. The next one we would move to would be 1212, and that gives us a distance of 857. Then we would move to 2296, and that gives us a distance of 1084. Then we move to 2800, which gives us 504. Then we move to track 544, which is a distance of 2256. Then we move back to cylinder 1618, and that gives us a distance of 1074. We move to cylinder 356, which gives us a distance of 1262. Then we move to 1523, which gives us a distance of 1167. Then we move to cylinder 3442, and then finally, we move to 4965, which is a distance of 3442, and then finally to cylinder 3681, which is a distance of 1284. So what was really important in this problem was that you got these numbers right. What was the order in which the cylinders would actually be accessed? And it's fairly simple in this one because it's first come, first served order. And so if we add up all the numbers, pointer back, if we add up all the numbers, you can see that our total will be 13,011. Okay? So when I'm grading this, what I'm going to be looking at, I haven't started the grading yet, but I should get that done fairly soon. But what I'm going to be looking at mostly is that you got the order correct as far as what tracks or what cylinders you were accessing next, because that's the important thing to understand for the algorithm. If you made simple addition or subtraction errors, I'm not going to take off points for that, as long as you understood the concept of what the first come, first serve algorithm does. Any questions on that? That one was pretty easy. Okay, the next one is shortest seek time first. Just like with first come, first serve, shortest seek time first, it really doesn't matter what direction the head was moving. What matters is what track is the closest, or what cylinder is the closest to where the head is currently positioned. And again, in this algorithm, the head's going to be moving back and forth, just depending on which cylinder is closest. So when I worked through this, I got the first cylinder that it should be accessing would be cylinder 2069, which is 81 cylinders away from the current position. Then it would go to 2296, which is 227 cylinders away. Then it would go to 2800, which is 504 cylinders away. So this was all a little harder to calculate because you had to kind of look at your queue over and over again to see, which one's closest, and be calculating the distance between where the head currently was and all the other positions that it had to move to find the shortest one. Sometimes you can just kind of eyeball it, but this algorithm kind of takes a lot of math in order to do it. Once it gets to cylinder 2800, it would move to 3681. After 3681, it would move to 4965. After it gets to 4965, it has to go all the way back to 1618, then to 1523, then to 1212, then to 544, then to 365. And so I did the calculations for all of these, added up the numbers, and I came up with 7,586 tracks. That's how far the head would move back and forth. Okay, any questions on that? Okay, so I actually find this one to be the hardest one to do, because you have to keep examining how far is it from the current head location to all the other tracks to figure out which one will be the shortest seek time. Now, of course, with shortest seek time first, the head is moving the shortest amount it possibly can each time. Okay, are you saying my answer is incorrect or your answer was incorrect, Monera? Your answer was incorrect. Okay, I haven't graded it. Did you get the tracks right? What order you were going to access the tracks? Did you just make a math problem, an addition or subtraction problem? Okay, you wrote the order and explained the concept. Okay, as long as you explain the concept and you told me that in your assignment, as long as I could see that you understood, I'm not concerned about if you added or subtracted incorrectly. Okay, it's more important that you understand the order That was the most important thing. And then whether you got the exact right answer is less important. Okay, that's why it's important to show your work so I can see, you know, what it is you did. And if you understand the concept but just make a simple error in a calculation, that's not a big deal. This is a computer science class, not a math class, so I'm more interested in the concept. He said, in this type, you arrange the numbers related to the shortest distance between the current head and the requested number. Yeah, actually, the order in the queue doesn't change. Okay, the queue is how they arrived. The queue is always first come, first served, or FIFO, I should say, first in, first out. So that's the order in which the request for reading from the disk arrived in the system. Okay, so the queue itself doesn't change, but the order in which the disk heads will actually access the tracks is what's going to change. Does that make sense? Okay. Okay, any other questions on shortest seek time first? Like I said, I think that was the hardest part of the homework, but was this particular algorithm. Okay, scan is the algorithm that's also called the elevator algorithm because it'll start at one edge of the disk and travel all the way to the other edge, and when it's done, it'll travel all the way back and just continue to go back and forth, reading any tracks that it needs to read on the disk. So it's always going from one edge to the other and reading any tracks that it needs to once the head passes over that particular cylinder. So this is where it becomes important what order, or what direction I should say, the head was already moving. In this case, the previous head position was 1805, and it's moving toward 2150, so we're moving from a lower numbered track to a higher numbered track. So we're starting at 2150, so the next track we want to move to is the next highest number, which is 2296. Then we move to 2800. Then we move to 3681. Then we move to 4965. And then we move out to the end of the platter. Okay, so it moved all the way to the very edge of the disk platter, the outermost cylinder on the platter. Once it hits the edge, it turns around, or it doesn't actually turn around, but it reverses direction and starts moving toward the lower number tracks on the platter. So the next track that it's going to encounter then is 2069. And now we're going to start going in descending order. Then it'll go to 1618. Then 1523, then 1212, then 544, and finally the lowest number, which is 356. I calculated the distances between all of those, and I added them up, and I came up with a total of 7,492. Okay? Now, once it read the information on cylinder 356, it would continue going back all the way down to 0, looking to see if there was anything else it needed to read. And then it would start going from 0 back up to the higher numbered tracks again until it hit 4,999. And it would just keep going back and forth over the disk platter. Any questions? Okay. Now look is very similar to scan. The only thing we do differently in look is we're not going to go all the way out to the edges. We're not going to go all the way out to the 4,999 track or all the way into the 0 track. We're only going to go, the head's only going to go as far as it needs to. And once it hits the highest number cylinder that it has a request for, it'll turn around or reverse direction and go in the opposite direction. So we start off the same way, where we access 2296, followed by 2800, followed by 3681, followed by 4965, and now the difference is we're not going to go all the way out to 4,999. It's going to immediately turn around, reverse direction, and go back to 2069, 1618, 1523, 1212, 544, and 356. And that will give us a total of 7,424 tracks, or the distance. That's how far that arm moved. Okay, so we can kind of see, if we look back at the scan again, we eliminated this move, and we eliminated a little bit of this move. Instead of going from 49.99, we started at 49.65 and moved back. So we were able to get a little bit shorter distance traveled with the look algorithm. Any questions on that? Okay. Now C-scan is like the scan algorithm, except what the C-scan is trying to do is say, okay, once I get to one end of the platter, it means once I get to one edge on the platter, I'm sorry, I got kicked out of Collaborate. For some reason, it dropped me out of the room, and so I had to get back in. Can you hear me now? Okay. Okay, yeah, I don't know why it does that, but every once in a while I get knocked out of the room, so sorry about that. So we were talking about the C-scan, and the C-scan, what that does is it moves it's always reading, in this case, from the lowered numbered tracks to the higher numbered tracks. And once it hits the end of the platter, it just reverses direction, goes all the way down to the lowest numbered track again, and starts reading. And so what it's trying to do is service requests that have been waiting the longest, because once we get to one end of the platter, you know that the ones that are at the other end of the platter, or the other end of the drive, are the ones that are going to have been waiting the longest. And so that's what it's trying to do. So even though we can see that the number here is a bit higher than we had with scan, it's a little bit fairer that it's going to these requests that have been waiting the longest for service, and always, you know, going from lowest to highest. So in this case, we would start again with 2296, then move to cylinder 2800, then move to cylinder 3681, then move to cylinder 4965, and because this is just C-scan, it would go all the way out to 4,999 before it would go all the way back to 0. So now in this one, the direction that the head was moving in the beginning of the problem is very important, because this tells us that it went from 1805 to 2150, so we know that it's only reading as it's going from the low numbered tracks to the high numbered tracks. And once it gets to cylinder 4999, it goes all the way back to 0. And so from 4,999, we go back to 0. Then we start reading again. It would service the information at cylinder 356, then 544, then 1212, then 1523, then 1618, then 2069. So when I add all this up, I end up with a total of 9,917. Any questions on the C-scan? The circular scan? Okay. So let's move on to C-look, which is very similar again to C-scan, but now it's not going to go all the way out to the edge of the drive, the edge of the platter. It's going to stop at the highest number track and then go all the way down to the lowest numbered request. So we start off the same way as we did with C-scan, where we will go to service the request for cylinder 2296, then 2800, then 3681, then 4965. Now the difference is it's not going to go out all the way to 499. Instead, it's going to go to the lowest numbered service request that it still has to process. And so it'll go down to 356. It won't go all the way down to 0, and then up to 544, 1212, 1523, 1618, and 2069. And so you can see this is a little shorter time, or a little shorter distance traveled, because it's a total of 9,137. So any questions on that? Okay, then let's move on to the information for this week. And here we're going to be talking now about the I/O subsystem in the operating system, what goes on in the kernel. And we're going to be looking at the structure of the subsystem, the principles and the complexities of the I/O hardware, the software performance of the hardware and software. Okay, because this chapter kind of ties together all these different things we've been talking about, because I/O is such a big part of what happens in a system, takes up a lot of the performance time, and so really a lot of the things that we've talked about, with the exception of some of the memory allocation, all has to do with I/O. Things get scheduled according to whether it's waiting for I/O or whether the information it's waiting for is available. Even actually memory would get allocated, because we have buffers and so forth that get allocated. So much of what a computer system does revolves around I/O and processing. Processing is kind of the part people don't really talk about very much, because the processing just has to do with, how fast your processor is and how well you write your algorithms. But with the I/O, there's all these different devices and all these different things that we can do to help improve the performance. So your book talks quite a bit about some of the different I/O hardware, and the important thing to realize is that there are lots of different I/O devices. You don't see it as much when you're working with a mobile device like a tablet or a phone, but when you're working with a PC, you can just think of all the different things that you can hook up to your PC. You have, disk drives, you might have tape drives, you have network transmission, you might have Bluetooth, you have a screen, you have a keyboard, you have a mouse, you have speakers, you have microphone, you have touch screens. I mean, just about anything can be hooked up to a computer, using a USB or something like that. And so we have all these different I/O devices, and there's more and more different kinds of I/O devices coming out all the time. But what you kind of want is for a programmer, for example, to not have to deal with all that complexity of all that different hardware. And you want all the hardware to kind of be accessed in the same way from an application's point of view. We also don't want the operating system having to know exactly how to access a particular type of hard drive or a particular type of tape drive or whatever. So there's all this other processing that takes place in what are called controllers. So these different I/O devices that we have communicate using a port. They communicate with the computer system using a port, and that's just a connection point to the computer system. There are buses that actually transfer data back and forth between the devices, and then there's this controller. The controller is really just another processor. You have your main processor, your CPU in the system, but all these different controllers also have their own processors in them. And so sometimes the controller is part of the device. It might be integrated. It actually comes with your hard drive or whatever. Sometimes it's a separate circuit board inside your computer. And the controller usually contains a processor, it contains some code, and it contains its own memory. So things like a hard drive might have an integrated controller that controls that particular type of hard drive, but then something like a monitor might not have a controller as part of it. That controller might be a video adapter that you have inside your computer. Okay, so we have all this different hardware that's an important part of the operating system, and part of what all this different hardware does is, in some cases, offloads some of the work that the CPU would have to do itself if we didn't have these controllers. Okay, so that's why the controllers are very important. Excuse me. Now, the way that the CPU talks to these different controllers is by writing bytes into the different registers for that controller. And it can do that in one of two ways. We have what is called programmed I/O, or programmed input-output, or memory mapped I/O. And so these are two ways of moving data between the devices, whether we're talking about a hard drive or a DVD or whatever, and main memory. You can use both types, programmed I/O and memory mapped I/O, in the same system. And what happens is when the CPU, when the processor, when what we think of as the computer wants to write out some data or get some data from one of the I/O devices, it writes bit patterns into the controller's registers. And when it's trying to get status, whether the read happened or the write happened, it then would read bits from the controller's registers. And so with programmed I/O, there are actually special instructions that will transfer a byte or a word to the I/O port. That triggers the wires that are the bus to select the correct device and then move the bits to that device's controller's registers. Okay, and that's how the CPU actually does moves 1 byte of data from main memory to the device, whether it be a hard drive or a tape or whatever. Another type or another method of moving data between devices, rather than doing this with these different special instructions, memory mapped I/O, and we'll talk about this later calling it DMA, memory mapped I/O, in this case, the device registers are actually mapped to the processor's address space so that the CPU, all it does is reads and writes to memory, and that gets sensed, and the device the device treats that memory as its registers, and the controller will act accordingly depending on what bits were set in these different registers. So we can look at what these registers are and what they do. We have a data in register that's associated with the controller, and the data in register is read by the processor to get input that was written there by the device controller. So when the CPU, when your program says to read data from a file, the CPU would actually tell the controller it wants to read something from the disk. Once the information is actually read from the disk, it gets put into the data in register, and then the processor, the CPU, actually reads that data, and that's how you get 1 byte of data from disk into memory. The data out register is the opposite. It's written by the processor to send output. Okay, so this is when your program is saying, here's something I want to write to disk. It sends, byte by byte, the processor sends it to the output, the data out register, and then the controller reads it from there and actually writes it to disk. Then there's a status register that contains bits that indicate the state of the device controller. And so the CPU actually checks the status register to see if the commands are complete, like if it said, do a write or do a read. It checks this status register to see if that command was completed. There'll also be status like byte available, saying that it was able to read a byte. The controller is saying it was able to read a byte from disk, so that byte is available for the CPU to then read. Or the status might be that an error occurred. So the CPU will keep checking the status register to see what's going on with the device and with the controller. And then finally there's a control register. And the control register is what's written by the host device to start a command or to change the mode of a device. Because sometimes devices can behave differently depending on how this control register is set. So, for instance, in communications, there's different things like full duplex and half duplex, whether the bits can move in 2 directions at the same time or only 1 direction at a time. And the control register would be used to set that for the device. So the control register is used to start something happening or to change how the device is actually working. So those are the registers that are used. And so we need to look next then at, well, how does the CPU actually know that something has happened? One way that the CPU can do this, and here I'm talking about the host, the main computer system, it will check the status register to see if the controller is busy or available before it tries to tell the controller to do something else. So it'll keep checking and checking and checking until the busy bit is clear on the controller for that particular device. Okay, so that's kind of a busy wait loop. It keeps checking and checking and checking. Say your program wants to read something to the drive. The CPU will have to see, well, can the drive actually, read something or write something, depending on what you want to do in your application. And so it'll have to check and check and check until finally it sees that the controller's not busy. because the controller can still be busy doing something from another program, another I/O request, and so forth. So the CPU has to keep checking until finally the controller is not busy. When the controller's not busy, the host will say, okay, I want to write something, so it'll set the write bit in the command register and write a byte out to the data out register, okay, if we're going to write to this drive. It would be the opposite if we were reading from the drive. We would say we want to read something, and then the controller would go out and read the byte that the CPU needed, and then the CPU would read from the read register, the data in register. But for a write, the host would then set the command ready bit saying that, hey, there's something for you to do, controller. The controller will see that command ready bit, and now it's going to say it's busy again. Okay, it was idle, now it's busy again. So it's going to read the write command from the command register, read the byte from the data out register, and finally write it to the device. Then it'll clear the command ready bit in the command register, clear the error bit, and clear the busy bit in the status register. So it did what it was asked to do. It wrote the device. As long as everything's good, it's now ready to get another command. If there were no errors, it would clear the error bit, and it'll also say it's not busy anymore. It's ready to get another byte or do whatever it is the CPU wants it to do. Okay? So you can see just to write one byte, there's all this stuff going on. So this kind of operation works well if the controller and the device are fast. But if the controller and device aren't very fast, data could actually be lost in your system. So you don't want to do this kind of polling unless you're sure that the device and the controller could keep up with how fast the CPU is telling it to read or write. Another problem with polling is that the CPU can spend all its time polling. And when it's going and repeatedly checking this status register, it's not doing anything else. It's going and checking, are you ready? Are you ready? Are you ready? And if it's not ready, it can get kind of stuck in a loop here, not doing anything, just waiting for the controller to be ready. Okay? So what some systems do, or most systems actually, is they use interrupts. And we've talked about interrupts a number of times, but now we're going to look at it at a little lower level than we've ever looked at interrupts before. You know, way back when, I think in Chapter 3, we talked about context switching and so forth. And so you can see here we're getting down to this is actually what happens when a context switch has to occur. So we have kind of this step-by-step process where, you know, the CPU has an actual wire that's an interrupt request line that the CPU senses after every instruction. So let's say that the CPU, you know, said to do some I/O. So it told the device driver that it needs to do I/O, and then rather than waiting for this particular I/O to complete, it will instead just be looking for interrupts, which is something that's done very, very quickly on the system because it's actually, you know, a hardware signal that happens when an interrupt happens. So the interrupt request wire is actually, or the interrupt request line is actually a wire. So it's going to get a signal on that wire when an interrupt happens. So it's more efficient than polling, which has to go out and look and look and look. Here, it's just going to get the interrupt. Once it receives the interrupt, it transfers control to the interrupt handler, and this is where context switching takes place. The interrupt handler processes the data and then returns from the interrupt, and then it goes back to resuming the interrupted task. So it's actually the I/O controller then that does the actual I/O And when it's done, it generates that interrupt. It sends that signal over the wire. Okay? So this is just another way that data gets transferred between all these registers. And these interrupts can be what's called non-maskable, which means they can't be turned off, or they can be maskable, which means the CPU is doing something really important, and so it doesn't want to be interrupted. So for a very brief period of time, it will turn off its ability to actually see these interrupts that are being generated. Okay, but the CPU doesn't like to do that very often because it doesn't want to miss anything that's happening. So maskable interrupts are only used before very critical instructions in the computer that can't be interrupted. Okay, the other way we can do it, besides doing the polling, we talked about how we could have the programmed I/O, which we just looked at. That was the special instructions to transfer the data. We could also do memory mapped I/O, and that's what we call direct memory access. And so with direct memory access, this is when the controller and the CPU kind of share memory, so that when the host or the CPU wants to transfer information from the main memory into the device, what it does is, instead of doing what we saw before and writing a command and so forth, all it does is it writes a command block to memory. And writing to memory is very, very fast. Now it shares this memory with the controller. So if we look here, what's going to happen is the CPU tells the device driver to transfer data to a buffer. The device driver tells the disk controller to transfer bytes. Then the disk controller actually does the DMA transfer. It sends each byte to the DMA controller. The controller transfers the bytes to the buffer, and then when it's all done, it interrupts the CPU to say that it does the transfer. Okay? So even though there's still a lot of steps here, it is a lot faster because the controller operates the memory bus directly. So it's actually putting addresses on the memory bus without using the CPU. It accesses that same bus that the CPU accesses, but it doesn't have to, it's this bus right here, this memory bus, but it doesn't have to actually interrupt the CPU to do it. Remember we talked about how memory, gets allocated and the CPU is what does that? Well, in this case, we're kind of bypassing that, having to go to the CPU every time to write to memory, because both the DMA controller and the CPU are accessing the same memory using this bus. Okay, so that's a bit faster. And of course, your book goes through all this in a lot more detail than I can in the short amount of time that we have. So all this stuff is going on under the covers while we're looking at it from an application interface. Okay, this is what we as programmers look at when we're actually working with the system. So usually, all the operating systems have different device drivers, and this shields the application from the device controller differences between the devices. Okay, so in your system, like if you have a Windows system and you hook up a new hard drive, or you get a new flash drive even, and you plug it into your USB port, you might have noticed where it might do some initialization where it's actually setting up the device driver for this particular device that you just added to your computer system. So there's all these layers of software that are between your application program, and your application program runs all the way up here above the kernel, there's all these layers between your application program and the actual devices. And so each layer here does some of the work so that you don't have to write all that stuff that we were just talking about with setting these bits and the different registers. You don't have to worry about any of that. You just say, I want to read data or write data. And that triggers the kernel to do something, which goes down into the kernel I/O subsystem, which then will activate the correct device driver, which will then communicate with the device controller, which then goes all the way down to the devices. Okay, so we have this whole layered interface. Now, all these devices, if you think about it, are very different. A keyboard is very different from a mouse, which is very different from a floppy disk drive, which is very different from a disk. And so what we're trying to do is make it so that at the upper layers in the operating system and at the application layer, it's very simple. You just read and you write. Down at the lower levels is where all the individual differences between these different devices come up. And so usually what happens is when somebody creates a new device, often they also write the device controller for every operating system for which this device can be used. Okay? So we have all this stuff happening in our system. Now, some of the differences between the different devices is how the device will transfer data. It can transfer data character by character or block by block. And character by character data is often things like a terminal, a keyboard, where you're not getting a whole record or even a group of records, you're just getting one byte at a time. A block device, like a disk, will read in a whole block or multiple blocks at a time. Some devices are sequential access, okay, like when you're doing communications over a modem, that would be sequential. Others are random, like a disk drive or a CD-ROM. How does it do the transfer? Here it can be synchronous or asynchronous, which is does it actually wait until the transfer is done? Or does the CPU go on and do other things while it's waiting for something to happen on the device? So for a tape or a disk, it would usually wait. For a keyboard, you don't want your CPU sitting there waiting for you to type something. Okay, that's a long, long time for the CPU to be waiting. So that's more of an asynchronous type of transfer. Sharing, is the device shared or is it dedicated? Can only one program use the device at a time? How fast is the device? And we've talked about, especially with disk drives, how they have the latency and the seek time. But then if we're talking about something like flash memory, we only have the transfer rate. We don't have the actually heads and the disk drive spinning. And then the I/O direction. Is it a read-only like a CD? Is it a write-only like a graphics controller that would control your monitor? Or can you do both like a disk? So we have all this complexity for all these different devices that somehow have to be handled by the controllers, by the device drivers, and then it starts getting more and more abstract as we move up through the kernel. So I already talked a little bit about block versus character stream devices. A block device transfers a block of data from the drive, or whatever the I/O device is, and that's where we're doing a read or a write or a seek. And this is where we're dealing with raw I/O, file systems or direct I/O, or memory mapped I/O. Okay, and we've talked about all these things before in this class. Character stream device transfers bytes one by one, and that has commands like get and put. And so really, when you're typing on the keyboard, it's actually transferring a character by character, but then buffers are often built on top of that so you can get line by line access And then that will allow you to do things like type in a whole line and hit enter, and before you hit enter you can still hit the backspace key to go in and edit it. That's because that line, those characters haven't been sent to the CPU yet. They're actually in a buffer, so that when you hit backspace it goes backwards in the buffer and then you can type again. Okay? So you get that type of thing with your character stream devices, that you can actually do line at a time access, which is a way of kind of buffering these characters that come in. Another, so I have a question here for you. Which of these are block devices and which are character devices? Okay, what do you think? Is a CD-ROM a block device or a character device? Do you read data in a block at a time or a character at a time? Block. Correct. Oops. So that's a block. Okay, what about a mouse? Is a mouse a block device or a character device? Character. That's right. You're doing mouse clicks. You're doing mouse positioning. What about a printer? Is that block or character, you think? Character. That's correct. Floppy disk. Okay. What's that? Block. Yep. What about a serial port where you're doing communications? What do you think a serial port is? Block or character? This one you're probably not as familiar with. Actually, it is character. It's a character device. Okay? You know, think about it if you're sending things through a modem. It's actually going character by character. What about an audio board? You know, where information's coming from. When you're playing music, is it going a block at a time or is it a character at a time? Okay, this is interesting because you kind of think, oh man, it probably has to put out a whole bunch of data at once, but actually, it's a character device. An audio board is a character device. If you think about it, you're talking about streaming. You know, you use that terminology because it's really just a stream of bytes that are going to play to make the music or the audio that you're hearing or that you're recording. So that is a character device. And then finally, a DVD is a block device. Okay, so I think you guys have a good idea about the differences between these two. Once again, I know we're running out of time, but I'm going to keep talking because I'm going to get through all my slides, even though I think I still have about 10 more to go. So if you have another class or you need to leave, this is being recorded, so you can just come back in at some point and view the recording. So I understand if you have to leave at this time. So to continue, another type of device is a network device, and network devices require a different interface than character or block devices. Here, what we want to do is use what's called a socket interface. Windows and Unix-based systems, they all include sockets, and those are used to send and receive packets over the network. So all this stuff we do on the web, all this information that you're getting from me right now, coming from my computer up to a server and back down to your computer, is all being sent packet by packet over the network. And so the web server actually is waiting for stuff to happen and moving these bytes all over the place. And it doesn't do polling and busy wait for network I/O. Sockets have what is called select, and that's how the server decides what socket, where the information is coming from that it needs to service. So if we're all going to a server that's running Blackboard right now, there are multiple sockets for each of our connections, and that's where I got bumped out. My connection was lost a little while ago, but it's listening on a socket, waiting for me to type something or click my mouse or do whatever it is I'm going to do. And so it's a different interface than what you would have with a hard drive, for example. There are other approaches besides sockets. There are things like pipes and FIFOs and streams and message queues, and all these are ways of talking to network devices. There are even in Windows, it has the concept of separating the network protocol from the network interface card, and you communicate with each of those separately. So there's lots of other things that that we need to be concerned about with I/O when we're talking about network devices. Another thing that we need to realize is that there's all this timing that's going on in the system. And we talked about this a while ago when we talked about, different scheduling and time slicing and what happens when a program's in a loop and how does it know that it's in a loop or it's hogging the CPU. So there are all these clocks and timers, and a clock is just another device that's part of your computer that'll give you the current time or the elapsed time, or you can even set the clocks, the timers to do something at a certain time. And we talked about this with time slicing. We have a programmable interval timer in our computer, and the CPU uses that when it does time slicing. Remember, it's going to give each process a different amount of time and just keep going in a round robin to all the different processes and letting them use the CPU for that amount of time. Okay? So we talked about that. We also talked about having cache, and you've seen disk cache and network cache even, that you have to clear at different times, and your system might use a timer, and when the timer goes off, it clears your cache. Okay, it doesn't hold those pages any longer. The network subsystem uses it to cancel slow network operations. Okay, and you may have seen this where you're waiting for something to happen, and your system times out waiting for network I/O. It happens sometimes with me when I'm downloading large files. It might time out waiting if my network connection is very slow. And then user processes, applications, can also use timers. Now, we've used a timer in this class. Can you think of an example when you used a timer in this course? When you actually used this device? Can anybody remember when you might have done that? Okay, to make a waiting time. Yep, in your sleeping teaching assistant program, you used a timer. Okay, to make a waiting time for the start of class. Yep, when you sometimes you might try to get into Blackboard and it won't let you in yet, because I've set it up so that Blackboard Collaborate will only start up at a certain time. That uses a timer. Okay, so there's lots of things that you use a timer for all the time. Okay, another thing that we need to be aware of when we're talking about I/O is blocking versus non-blocking I/O. And you're going to do your homework based on the concept of blocking and non-blocking I/O. So let's just make sure we understand what that means. And here with blocking I/O, blocking causes the application to wait until the operation is complete. It's used when the process must wait for something to happen before it can continue. And so this is something like when you're in your application, you want to read a record from a file. Okay, you want to look something up in a file. So blocking I/O would be your program says read something, and it's just going to sit there and wait until that information is read. So when you're doing things like reading from tape or disk or something like that, you're actually waiting kind of for one specific thing to happen. You're waiting for a read to happen. And we kind of talked a little bit already about how things work when you're blocking, where a process would request I/O, then the device driver would handle that request. Eventually, there would be an interrupt that, well, it wouldn't do an interrupt now, but it would actually do the data transfer, then cause the interrupt to occur. The data would come back to the device driver and then get back to your process. So here you tell it to read or write, and all the time it's doing this transfer and transferring the data back, and when there's an interrupt and so forth, all that time your process is waiting. So that's blocked I/O. Your program can't do anything until it gets the record that it's read. Non-blocking I/O, on the other hand, doesn't cause the application to wait until the operation is complete. And this is used when the arrival of data is unpredictable, it can take a varying amount of time, or it'll come from multiple sources. And so a lot of times non-blocking I/O is used in cases like if this was a network server. There's going to be input coming in from all these different people who are connected to the network, and you don't know, what address the next byte is going to come from on your network. And so that would be an example of the arrival being unpredictable. Okay, if you have class, just leave, and I will continue recording so you can see the rest of the presentation. Okay, have a good day. So non-blocking I/O is for things like networks. Another thing would be if you're doing things like you have a GUI, a graphic user interface, and there you have things being written to the screen, it's monitoring the mouse, it's monitoring the keyboard, and things could be happening with all these devices at the same time. You don't want the hardware to be, or the CPU to be sitting there waiting for you to click a mouse when you're actually typing on the keyboard. Okay, you want it to be saying, okay, I'm going to wait for a mouse click, but if there's no mouse click, I'm going to check the keyboard and see what it's doing, and if the keyboard's not doing anything, I'm going to be writing things to the screen or whatever. So there's multiple sources where I/O is happening in a graphical user interface. And that would be an example of a non-blocking kind of I/O situation. Okay, so here you issue the request, it goes to the device driver and to the hardware, but then it immediately, the process can immediately be rescheduled on the CPU. It can be immediately allocated to the CPU because it's not going to wait for something to happen. Once something happens, though, then an interrupt will occur. We'll take this path and it'll interrupt, and the interrupt will then tell the requesting process that something happened. Okay, so if you're sitting there at your system and you have a graphical user interface and it's looking at the keyboard and nothing's happening, and it's looking at the mouse and nothing's happening, so it's drawing stuff on the screen, as soon as you click the mouse or hit the keyboard, it's going to trigger an interrupt and get the attention again of that application and say, oh, okay, well now you need to, the GUI needs to read from the mouse or read from the keyboard. Okay, so those are some of the differences. Now, when you're writing an application program, it's very easy to write something where you say read, and it just sits there and waits until the data comes. Okay, that's easy, and that's what you do in blocking I/O. It's more complicated, however, to do non-blocking I/O because you have all these things that can be going on, and your application program or whatever code that you're writing can be off doing other things when this interrupt occurs, and it has to say, oh, that's right, I was looking for the mouse to do something, and then you have to jump over to the code that handles the mouse requests and so forth in your application if you're writing a GUI application. Okay? So you know, there's trade-offs between the two. Some devices are better with blocking I/O, and some devices are better for non-blocking I/O. But then how your application has to handle everything is different. It's a little more complicated with non-blocking I/O versus blocking. And that's kind of what your homework problem asks about. I changed the wording a little bit here from what it said in your book, because sometimes I find your book to be a little confusing in what it's asking. And so what it's really saying is, give me 3 examples in which blocking I/O should be used. And we talked about that. You know, that things like, you know, hard drives use blocking I/O. And that's all I'm looking for here. Which kind of devices would be using blocking I/O? And then give me 3 examples of when non-blocking I/O could be used. And it talks about these in your book as well. And then the question is, why not just do non-blocking I/O and have the processes wait until their device is ready? In other words, why do blocking I/O ever? Okay? And when you're answering that part of the question, I gave you some things to think about. Is non-blocking I/O easier or harder to program? And why? And is the performance of non-blocking I/O better or worse? And why? And when you think about those things, then you kind of have the answer to this part of the question, why you wouldn't just do non-blocking I/O. Because there's times when blocking I/O is, you know, more efficient or is easier, and that's kind of what I'm looking for in this question. Okay? Any questions on your homework? So we've talked about it. I think it's going to be pretty simple for you once you've done the reading and you kind of understand these things that I've been talking about. You'll be able to easily give me 3 examples of blocking I/O, 3 examples of non-blocking I/O, and then just think about why you would use blocking I/O versus non-blocking. Okay, why we have both kinds. Any questions on that? Okay, the example can be without details. Yeah, if you just tell me, you know, some examples, you can give me the examples, you know, like say, reading from a hard drive would be an example of blocking I/O. Okay, and I'll know what you mean there. Okay. Any other questions? Okay, so that takes us to the I/O kernel subsystem, which we've talked about a little bit. And now what you're going to see is all this different stuff that we've been talking about throughout most of the course happens in the kernel I/O subsystem, again, with everything that we've talked about so far except for memory allocation and what actually happens in the processor. There's a ton of stuff that happens in the kernel I/O subsystem. So the kernel I/O subsystem is what coordinates all these services that are available to application programs and to other parts of the kernel. So the kernel provides a service to schedule I/O. Okay, and you know, it keeps track of the statuses, the device status, and what's available and what's not, and so forth. It provides for buffering, caching, and spooling. And buffering, we've already talked about a little bit, where you would read a record in, or you would read a block or multiple blocks into a buffer, and then they could be read more quickly as the application needs the data. Caching you know about as well. Spooling, you may not be familiar with that term, but that's when you're actually sending something to a device like a printer. It's actually a way of buffering the file. And you might have noticed that when you're working on your computer, you might send a file to the printer, and it takes a little while because it's sending it to the printer, but then it's kind of in the print queue. All the data's been written out by the CPU, but it's actually been being held by the spooler, and it will be written to the printer, but you can go off and do other things. Okay, your application doesn't sit there waiting for the printing to happen. Okay, and that's what spooling is about. The kernel I/O subsystem is responsible for allocating what devices are being used by what processes. It monitors the devices. It handles errors from the devices. It recovers from device failures. It controls the access to files and devices to make sure, if it's something like a tape, only one process can be using that tape drive at a time, so it'll control that type of thing. It controls what operations are valid for each device. In other words, I can read and write to a hard drive, but I may not be able to write to a CD-ROM. If it's just a regular CD-ROM, it's not a read-write CD-ROM. Okay, so the I/O subsystem would take care of that. Hala said spool, it's used as a reserved word in some programming languages to deal with the printer. Yep, you spool things to the printer, but you don't see that as much these days where you handle the spooling in the application program. That's often handled kind of under the covers by the operating system with the I/O subsystem. The kernel also takes care of managing the namespace for files and devices. Remember, all our files have names, even our devices have names, and the kernel manages that to make sure you don't have two files with the same name in the same directory and that type of thing. It allocates file system space, which we talked about, quite a bit in previous chapters in our book. And then it configures and initializes the device drivers. So really, there's all these different things that the kernel subsystem has to do. And it does a lot of these things as it's servicing our I/O requests. And your book goes through a nice example. I'm not going to necessarily go through this all step by step because we've talked about it in different ways kind of throughout the course. When you do a request for I/O in an application, that does a system call. The system checks to see if it can satisfy the request. If it does, it transfers the data, and then it'll return from the system call. Otherwise, it sends a request to the device driver, does the blocking if it needs to, processes the request. The device controller gets involved. When the device is finished, it generates the interrupt, which then will, again, move up the stack to the interrupt handler, to the device driver, transferring the data to memory, and then finally your process would be signaled that your I/O was complete. So I really like this because it ties together all these different things that we've been talking about, all these different pieces that we've been talking about. Okay, so you might want to spend a little bit of time, in your book. It goes through this step by step and what's happening at each step of the way. And it's kind of interesting, to look at because we've talked about all this stuff and you can see how complicated this all is. Okay, in addition to the type of I/O we've been talking about, Unix has another type of mechanism called streams, which is another way to interface between a user process and a device. Okay, we looked at this process here that we're kind of familiar with already. Unix System 5 has a different method of doing it, and it's kind of interesting just to see that there's different ways to do the same kind of thing. We have a user process here, And there's a connection between the user process and the device. And this connection has what's called a stream head on one end and a driver end on the other end. And then we have a bunch of read and write queues in between. And these are called modules. These modules have these read and write queues. And so in this type of system, the user wants to do some kind of I/O. It will communicate with the stream head, and that'll communicate with these different modules, which will eventually communicate with the driver. The driver communicates with the device, and then sends the data back up through these different queues. Okay, so your book goes through this, just because to show you kind of there's more than one way of doing this, even though the way I showed you with the I/O processing is the more common way. This is kind of an interesting way that the user process can communicate with the device. Okay, the last thing your book talks about then is performance. I mean, we've talked about all these different things that are going on every time you want to write. I mean, we don't even think about, clicking the mouse or reading from disk or typing things on the keyboard. But now that you're familiar with all these details in the operating system, it's just amazing all the stuff that's going on just for something simple like a mouse click. And we kind of take all this for granted. But you can see how with everything that's going on, the I/O in a system is going to have a big impact on the performance of your system. Because the CPU has to execute the device driver, it has to schedule processes as they block and unblock. There's all kinds of context switching that's going on with all these interrupts that are going on. And even more so than with disk or other I/O devices, with network traffic, there's a lot of interrupts. Think about when we do things all the time over the web, and that's causing interrupts all the time as data is coming to your system or flowing out of your system. And then there's all this data that's being copied. It's being copied between the controllers and memory, between buffers and the application, and the data is just being copied all over the place. So we have to look at, how quickly can we switch contexts, how often do we switch contexts, and how much are we copying this data? How often are we copying data, and how much data is being copied at any one time? So all these things are going to affect the performance of your system. The way we can improve performance is by reducing the number of context switches, and there are different ways you can do that in the operating system as well as in your program itself. You might want to design your code in a way to take advantage of, let's say things like, reading in a lot of data at once rather than reading it in, a byte at a time, and sometimes you can choose that. When you're actually choosing what I/O command you're using. You can, in the operating system, you could reduce the number of times data is copied. We looked at, for instance, DMA, direct memory access, where the data didn't need to be copied. Both the controller and the CPU were accessing the same memory, so we wouldn't have to copy it so many times. We can look at how we can reduce the number of interrupts, and this is where I'm saying you can transfer a large amount of data. We can use smart controllers where more processing is actually happening in the controller rather than the CPU having to be interrupted all the time. And we can do polling. I already mentioned using direct memory access to reduce data copying. We also can do things in parallel. In other words, get some of your instructions, rather than them being software that uses the CPU, get some of these low-level operations actually down into the hardware so that the controller can run things in parallel with the CPU, because it's a different processor and different hardware, and we can actually have certain commands or operations be actually in the hardware itself, so we're not using the CPU. And then the other thing that's done to improve performance of I/O is do load balancing, where you're balancing the CPU and the memory subsystem, which we talked about when we talked about memory allocation, the bus performance, where data is being moved, and the I/O performance. So you don't want the CPU to be waiting for any of the I/O devices. You don't want the I/O devices to be waiting for the CPU and so forth. So one of the things you do in an operating system is try to get this nice balance of the workload so that everything is being utilized at the highest degree possible. Okay? And now you can kind of see how complicated that must be now that you're starting to understand all these internals of the operating system. Okay, and we talk about it, especially in terms of I/O, because there's so much in the system that gets affected when you're doing I/O, and I/O is done all the time. That's the only way that we interface with the computer, and how we get data in and out of the computer is through the input and output through the I/O. Okay, so that's what we had for this week. Any questions on any of that? Okay, just remember that if you haven't done your programming assignment, that's due at the end of this week, as well as your week 10 exercise that we talked about in class. If you have any questions on any of these materials or any of your assignments, please feel free to email me or post something out on the discussion board. If there are no other questions, I'd like you to have a good evening, and I will see you next week. Michelle, I'm sorry, I don't understand Arabic. You're welcome. No problem.